Hello everyone, I'm Minori Shikauchi from the University of Tokyo, and I'm a PhD student at the university, and I'm so happy to talk to you today. And today I'd like to talk about some results we obtained in the latest investigations, which is theoretical perspectives on proving black hole population with the astrometric satellite Gaia. So before entering details, I'd like to share what is the motivation for these works. And as some of you may know, the astrometric satellite Gaia can observe binaries consisting of luminous companions, LCs, and black holes whose orbital period is larger than years, which is amazing. So because the current observational way is somehow biased to short period binaries like X-ray and gravitational observations. Thus, observations with Gaia may reveal different black hole populations from what we've seen in the current observations. So for now, we focus on how many such long orbital period binaries can be observed with Gaia and what properties can be inferred if we observe such binaries, such as where they are born, how they evolve to black hole binaries, and binary and spatial parameters correlate with each other. So that is the motivation for our works. Okay, so here's the contents of this talk. First, I will briefly introduce what is expected for Gaia. And then I will overview 3 papers. One is investigating the contribution of cluster origin black hole binaries. And the second is systematical investigation of the dependence of binary evolution parameters on the detectable number of black hole binaries. And finally, I will give a brief advertisement of our recent paper, which investigating parameter correlations of detectable black hole binaries. So if you have any questions, please feel free to ask me. Okay, so let's move to the introduction. So what is expected for Gaia? So Gaia mission is a scientific mission driven by European Space Agency, which is launched in December 2013 and has been observing since July 2014. And initially, this observation was expected to last 5 years, but now the period is extended to longer. And the observational way is called astrometry, which is by combining with photometric and spectroscopic data, Gaia obtains 3-dimensional position and velocity of a source with such a high angular resolution as about 10 microarcsecond. So by astrometry, how can we obtain binary parameters such as component masses, orbital period, and so on? So here's the principle of detecting binaries by astrometry. And so this figure shows an example of a motion of luminous companion. Here it is called a visible star. And as you can see, if you observe motion like sinusoidal motion like this, and you may think this is caused by the existence of an invisible companion like this. And if it is the case, we can write an equation which is based on Kepler's law, which includes binary parameters like masses of the unseen object and the luminous companion, and a semi-major axis and an orbital period of this binary. And we can estimate some of the parameters, like from this sinusoidal motion, we can determine the orbital period P, and we can also obtain from the motion of this visible star and the parallax of it, a semi-major axis from center of mass to secondary, which is corresponding to this length. And also, we may be able to estimate the mass of luminous companion from its spectra.
Can I ask a question?
Yep.
So, in general, you're only looking at the binary projection, right?
Right.
So, do you have enough information from just the astrometric motion, or are you also relying on spectroscopy to break the degeneracy between the semi-major axis of the binary and the inclination angle?
Yeah, I think by combining spectroscopic and photometric data, we can resolve the degeneracy of inclination. And yeah, so I think the function, which is called mass function, should be degenerated with inclination angle in spectroscopy. But combining photometric data, we can resolve the degeneracy.
And one more question, if I may. So you point out that you can get the mass of the luminous companion.
Mm-hmm.
Now that presumably requires stellar modeling.
Yeah.
Now, of course, this being a binary, there's a concern that the binary has gone through some interactions, and that as a result, the star may not be the same as a single star would evolve, right? So,
yeah.
So to what extent are you concerned about the fact that your star doesn't follow the corresponding diagram tracks that a single star would, and therefore you could be, I mean, certainly, there have been plenty of examples in the literature in the last 2 years, right, of people misinterpreting detached binaries because something that looked like a B star was in fact not a normal main-sequence B star, but was a stripped helium star that had a similar appearance to a B star, but a totally different mass, right?
Right. Yeah.
So how much should we worry about those kinds of things?
So yeah, I'm sorry I can't share to what extent the effect of binary interaction affects the estimate of luminous companion mass, but yeah, but I think if we do enough follow-up observation, we can reduce to some extent the uncertainties on luminous companion mass. Yeah. Okay. So then, by using the estimated binary parameters and combining the equation I showed in the previous slide and the center of mass equation shown here, we can estimate the mass of unseen object. So even if we can't observe the invisible companion, we may confirm the existence of the unseen object swinging around the luminous companions. So this is the principle of detecting binaries with astrometry. So also, I'd like to share the status of the current black hole observations. So this is a famous figure drawn by a member of LIGO team. And as you know, there are 90 gravitational waves from binary black holes, and there are about 60 black hole candidates in the galaxy until 2020. And also there is one black hole and all-type star binary with an orbital period is about 10 days, which is found in spectroscopy. So as we've seen here, as the orbital period of gravitational wave progenitors and detected black hole binaries is much short, such as hours to tens of days. So which means the current observational way is somehow biased to shorter period binaries. So as we see, the Gaia may observe black hole and luminous companion binaries with orbital period is much longer than the gravitational wave progenitors and detected black hole binaries, which is much longer than the orbital period of the detected black hole binaries. So we expect Gaia may reveal a different black hole population. And so before entering showing some results obtained from Gaia, there are some questions about the possibility of Gaia. So which is how many such long period binaries can be detected, and what properties can we estimate if they detect such binaries. And so if we don't have any questions, I'd like to share the result of our first paper, which is investigating how many cluster origin black hole binaries can be detected with Gaia. So here I'm summarizing the results of the theoretical researchers theoretically estimating the number of detectable black hole and luminous companion binaries with Gaia. But please note that these results assumed all the black hole binaries originated from isolated fields, which means, as you can see this figure, the initial binaries born as binaries and evolved without any dynamical interaction like this. So at that time, no one considered black hole binaries evolving during dynamical interactions with other stars, which can be happening in dense stellar regions. So in the stellar dense region, you can see a binary consisting of black hole, this black ball, and by dynamical interaction, the binary can exchange its companion and then obtain another companion like this. And naively thinking, in such region, stellar number density is higher than in isolated fields, which means more binaries can be formed. But there is a difficulty of observing such black holes. But so because if they're remaining in such region, we can't resolve it. So so for the later analysis, we assume we can only observe binaries kicked out from the regions. So so in the following slides, I will estimate how much dynamically formed black hole binaries contribute to the detectable number of black hole binaries, and discuss whether we can find any differences of formation process by the observations. So here is the setup for the models in n-body simulations. So here, as a dense stellar regions, we focused on open clusters. And here's the setup for open cluster models. And we fixed metallicity as a single value, which is solar 1. And also, this is the initial mass of each cluster, which is 2,500 solar masses. And also, we employed a Plasma profile for the density profile in the cluster. And also, we assumed all the stars start from single stars, which means we didn't include any primordial binaries. And each star follows a Krupa initial mass function, which is a power distribution with a range of 0.08 to 150 solar mass. And also, we neglected the existence of Natal Kick for simplicity. So some of you may wonder why we focused on open clusters, not globular ones. There are two reasons for this. And one is open clusters are typically located closer to us, which enables us to detect black hole binaries more easily. And also, the other reason is open clusters are younger than globular ones, which means massive luminous companions, which are more luminous than light ones, can survive in open clusters. And we did 1,000 different realizations with N-body simulation code, which is N-body 6++ GPU developed in this paper. This code can track binary star evolution as well as single star evolution. They are basically based on BSE, which is invented by Hari et al. And from these simulations, we obtained black hole and main sequenced binaries kicked out from the cluster models. Yeah.
So I'm curious about the assumption of no primordial binaries, because I would have actually thought that open clusters would be kinds of places where, I mean, if we actually assume that much of the star formation in the universe is happening in open clusters, right? Then you know, the binarity we see today must ultimately be coming from these systems, and I'm not sure if you assume no primordial binaries, would you be able to reproduce the very high binarity multiplicity fraction of the observed stars? So I would have thought that you need to rely on some binaries being already formed, you know, in the pre-made sequence phase, rather than just being formed through later dynamical interactions.
Yeah, yeah, agree. But the motivation for this work is we'd like to see the effect of dynamical interactions. So if we include any primordial binaries, this won't, maybe the result won't reflect only the effect of dynamical interactions. So yeah.
I guess the curious question is whether the combination of the two is interesting, right? So, so whether you want to, you know, whether it's worth thinking, and I think there, I mean, in a different context, but I think there was a recent paper by Subharan Banerjee and Chris Luchinsky and Alexandra Olejak, who I think were sort of looking, they were interested in spins rather than of the black holes rather than detached binaries, but they I think we're sort of arguing that actually in open clusters the combination of dynamical interactions and regular binary, isolated binary evolution might be interesting.
Yeah, I agree. So yeah, it would be better to include any effects of primordial binaries or Natal Kicks. Yeah. Yeah. Okay. So so I'd like to explain what is binary evolution. So there, so here I mentioned I'd like to mention about 3 effects of binary evolution. So first, a star can blow off its envelope, and if it is included in a binary system, the blown off envelope can be accreted to the other star, and which can transfer mass and angular momentum to the other star. And also, if such mass transfer becomes unstable, the binary can enter a phase called common envelope, which shares one envelope with 2 stars, like this figure, and they finally, the binary can survive if the envelope totally expel, or the binary can merge, like this. And also, finally, I'd like to mention about Natal Kick, which is due to asymmetries of supernovae. And sometimes the asymmetry can kick a black hole, which leads the binary to disrupt or change its orbits. So from here, I'd like to share how to estimate the detectable number of black hole and luminous company binaries from the simulations. So first, we assume the number density of black hole and main sequence the binaries in the Milky Way can be written as this equation. So here, where this M tilde is the number of black hole and main sequence the binaries obtained from the simulations, and TMS is the lifetime of main sequence star, and this rho dot is the local star formation density. And for this rho dot, we assumed it is proportional to the current local stellar density of the Milky Way disk. So, so here we only considered about the Milky Way disk because due to interstellar extinction, we can't observe the Milky Way bulge. And also, this rho dot should be proportional to these 2 factors, where FCL is a fraction of stars formed in the clusters. And based on the observations, we estimated which is roughly 0.1. And this RSF is also a constant, which is star formation rate, 3.5 solar mass per year. And so by using this number density of black hole binaries, by integrating this number up to the maximum distance called Dmax, we can obtain the number of detectable black hole and main sequence the binaries can be like this equation. And where Dmax is the maximum distance to a binary where it can detect it with Gaia, so which depends on the detection criteria we used and binary parameters like black hole and main sequence the masses, orbital periods, and so on. So here I summarized the detection criteria we employed here. So first of all, the first criterion doesn't directly determine Dmax, but this is also important criterion, which is the orbital period of the detectable black hole binaries should be within this range, 50 days to 3 years. And the lower limit, 50 days, comes from Gaia's cadence, and the upper limit is required for required for an accurate estimate of the orbital period. And so these three criteria directly determine the max, and the first criterion requires to detect luminous companion. So which is the apparent magnitude of a luminous companion should be smaller than the limiting magnitude of Gaia. Also, we have to consider about interstellar extinction. Also, the second criterion is we should estimate the distance to a binary D accurately based on the parallax. This is the error of the estimated distance, and also this is the distance to a binary. And finally, the last criterion, which is the orbital motion of luminous companion, should be determined accurately, which is the most strict criterion in our work. So by using these detection criteria, we estimated the number of detectable black hole and main sequence binaries. So here is our result. We estimated about 9 black hole and main sequence binaries can be detected with Gaia during 5-year observations. So for comparison, I showed the results of isolated field binaries, Yamaguchi et al. 2018, which employed the same detection criteria. And they estimated about hundreds to 1,000 binaries can be detected, but there are some caveats. They employed some approximate models for black hole mass distributions, and they employed some different models for binary evolution. So also I'm showing the result I'd like to share for the next section, which employed isolated field binaries, and we estimated it's about several to dozens of black hole and luminous companion binaries can be detected. So if we compare the results of this and the estimated value here, the contribution of open cluster binaries is not negligible to that of isolated field binaries. And there is one more thing interesting to mention. That is, almost all of the detectable black hole binaries reflect the effect of dynamical formation process. So like this. So I'm showing here a schematic figure of an evolutionary path of the detectable black hole binaries. So after forming a black hole, a binary including black hole and some main sequencers enter common envelope phase, and then they evolve to tight black hole and post main sequencer or some compact binaries. And so here, what is notable is that they experience a binary and single interaction, which cannot be happening in isolated fields. Then they evolve to black hole and main sequence binaries, and then move away from the clusters. So the detectable binaries finally capture companion main sequencers by dynamical interactions, which means main sequencers should not be polluted by outflows of the black hole progenitors. So on the other hand, the companion main sequence stars in isolated field binaries can be polluted by black hole progenitors. So we like to conclude that follow-up observations of main sequence stars may reveal chemical components leading to the formation process of black hole and main sequence binaries. So this is the main result of the first work. Yeah, Ilya.
Sorry, two questions. So one is, did you also consider the possibility of 2+2 interactions rather than 2+1 interactions? In which case the new companion might itself have still come from a binary, not this binary, right? But it might still be polluted by some interactions with its binary companion. Maybe I'll let you answer that, and then I'll ask my second.
Yeah. So you're mentioning about the final main sequence, the companion can be polluted by other black hole progenitors.
Or just other stars, maybe not ones that make black holes, but just other stellar interactions.
Yeah, I think that can be happening. So, but yeah, actually, this is just by analogy of X-ray binaries, and we didn't see carefully about chemical components of these stars. This is just an estimate, actually. So, so we should check chemical components of these stars if we really want to know the effect of other black hole progenitors or other stars.
And my other question is, do you expect that at the time of the Gaia detection, your cluster is still in existence? And if so, is there a chance to try to track back the binary to the progenitor cluster, right? So when you see the binary, Gaia is telling you, something about its, well, of course, its location, but also its velocity as a binary, right? So can you actually try to track it back and say this is the open cluster it came from?
Yeah, I think we can maybe. But if the original open clusters disrupted when we observe the binaries, we not be able to determine which is the origin of the binaries. Okay, so if we don't have any questions, I'd like to move on to the next work, which investigated dependence of binary evolution parameters on the detectable black hole and luminous companion binaries. So here again, I summarized the results of previous works and also the number of binary evolution parameters they employed, such as supernova models, combined Bell phase parameters, and Natal Kick models. And here you can see previous works investigated just one or two combinations of these binary evolution parameters. So the aim of this work is to investigate how all the combinations of these parameters affect the number of detectable black hole binaries, and also discuss whether we can determine we can give some constraints on binary evolution parameters from the observed binary parameter distributions. So here we employed isolated field binaries and then simulate their binary evolution by using binary population synthesis code BSE. And we updated its zero-wind models to the results in Belczynski et al. 2010, which which is a metallicity dependent formulation. And also this code can trace binary evolution with binary interactions, like which I have shown, like mass and angular momentum transfer and common envelope phase and so on. So from the next slide, I'd like to share what kind of binary evolution parameters are used in this work. And okay. So before entering the details of binary evolution parameters, here is the initial setup for BSE, and we assumed all the binaries start from zero-age main sequenced binaries, and we employed the same primary mass distribution in the previous work, which is Krupa initial mass function. And also we employed a flat mass ratio distribution, which is independent of the mass ratio, which is the ratio of secondary to the primary. And also a logarithmic flat distribution of initial symmetry axis was employed, and also we fixed a metallicity value to the solar one. And based on these setups, we simulated 10 to the 6 binaries for each parameter set, and we employed 12 parameter sets consisting of 2 Supernovae parameters, 2 Supernovae models, and 3 common envelope efficiency values, and 2 Natal Kick parameters. So, so from the next slide, I would like to look into the details of binary evolution parameters. So first, I'd like to mention about a Supernovae model. So as X-ray observations shown in this figure implies the existence of lower mass gap colored in a light blue region and in mass black hole mass distribution. And so in order to discuss whether this lower mass gap is intrinsic or not, we employed 2 super models suggested in Fryer et al. 2012, which are called the rapid and the delayed models. The right figure shows the relationship between the black hole masses and their age main sequence masses in a single stellar evolution. And as you can see, in the rapid model, such lower mass gap black holes cannot be formed. On the other hand, in the delayed model, such black holes can be formed. So okay, next, for common envelope efficiencies, we employed 3 values. And in this simulation, common envelope evolution is defined by this equation, and where the surfaces 1 and 2 correspond to the primary and the secondary star, and those of F and I are showing the final and the initial state. And these equations include 2 parameters, alpha and lambda. And here we used for lambda, which is dependent on the structure of the mass donor, and we employed the values shown in this paper. And here, alpha determines how efficiently the orbital energy can be converted to expel the common envelope. And here we employed 3 values, 0.1, 1, and 10. And if the body becomes larger, that means the binary can expel its common envelope efficiently and is more likely to survive. And finally, I'd like to introduce parameters of Natal Kick. So, so black hole Natal Kick is still controversial, and we adapted the model called fallback kick and switched it off for the comparison. And what is fallback kick model? So that is the model where the strength of the kick modulated by the fraction of fallback matters to the total ejected matters defined as FB. And the definition tells us the fact that the fewer matters fall back to the black hole, the stronger Natal Kick becomes. So coming back to the relationship of black hole mass and zero-age main thickest mass, as you can see, light black holes formed in the delayed model tend to suffer large Natal Kick and tend to disrupt. Okay, so by using 12 parameter sets, we obtained black hole and luminous component binary populations, and then applying the detection criteria I showed in the previous section, we estimated the detectable number of black hole binaries. So here I summarize the number of black hole binaries, and yeah, please note that we extended the upper limit of the detectable orbital binaries to 10 years from 3 years. So here you can see we estimated about 1 to 46 black hole binaries can be detected during 5-year observation. And we can see some dependencies of the number on binary evolution models. Like if we compare the number in in different choice of alpha, you can see the number of detectable black hole binaries increases if we choose a larger value for alpha. So that is because if the common envelope efficiency is high, the number of surviving black hole binaries after the common envelope phase increases, which greatly contributes to the number of detectable black hole binaries. And this trend can be seen in both supernova models. And also, this is only seen in the derived model, which is dependency of the choice of Natal Kick. And as you can see, if we compare the results with no kick and with fallback kick, the detectable number greatly reduced if we employ a fallback kick model. So that is because the fraction of fallback matters in the derived model is smaller than that in the rapid model. And thus, black hole binaries suffer from non-negligible Natal Kick and tend to disrupt. And this trend cannot be seen in the rapid model because of the reason. So, okay, so from the next slide, I will show some implications for the observations, like showing the binary parameter distributions. So these figures show the black hole mass distributions, and the black and the red lines correspond to the distribution of the detectable black hole binaries and the galactic black hole binaries. And for comparison, I showed the distribution of black hole mass obtained from single-stellar evolution as a blue dot line. And as you can see, the distribution of the detectable black hole binaries and the galactic black hole binaries are so similar. That is because we thought we employed a single metallicity value as solar metallicity, so which leads to mass loss rate is high, and which can blur the effect of binary interaction. So that is why the three distributions are so similar. So, and as you can see in the rapid model, any lower mass gap black holes cannot be detected, while lower mass gap black holes are formed and also becomes detectable in the delayed model. So we concluded Gaia will observe such lower mass gap black holes if such mass gap is not intrinsic. Okay, so and also there is another implication for the observations, and yeah, so in these figures I'm showing the distribution of the detectable black hole binaries with a different choice of common envelope efficiency alpha. So the black line shows a smaller value of alpha, and the blue line corresponds to the model with a higher common envelope efficiency. As you can see, with a high common envelope efficiency case, binaries with light luminous companions and short periods can be detected. So that is because with a high common envelope efficiency case, binaries with light luminous companions can easily expel the common envelope and then survive, and then contribute to the detectable number. So the another implication is that a higher common envelope efficiency should be favored if we observe tight black hole binaries with light luminous companions than one solar mass or something. So that is the conclusion of the second paper. And if you don't have any questions, I'd like to move on to the final paper, which is recently accepted by APJ, which investigating parameter correlations of detectable black hole binaries. So this work is motivated by X-ray observations, and these figures are showing some parameter correlations between black hole masses and the distance from the galactic plane, and orbital periods, and the distance from the galactic plane. So you can see there are some anti-correlations between these parameters, and we focused on the detectable binaries with Gaia, whether we can detect such correlations of the detectable black hole and luminous companions with Gaia. To that end, we have to simulate a spatial distribution of black hole and luminous companion binaries. So we theoretically estimated the spatial distribution for the first time. So here is how to get the spatial distribution of black hole and luminous companion binaries. So first, based on the Milky Way model employed in this paper, we generated 10 to the 7th initial binaries, and then simulated their binary evolution with BSE, and then obtained black hole and luminous companion binary population. And finally, we numerically calculated a motion of each black hole binary in the Milky Way potential. So here is the Milky Way model we employed here, so which is empirically informed analytical model employing meteoricity radius time relations in this paper. So we assume the Milky Way consisting of 2 disks, thin and thick disks, and also bulk components. And for each component respectively, we considered star formation histories, spatial distributions, and meteoricity distributions. So this is an example of the spatial distribution of initial binaries. And also, so we tracked a motion of black hole and luminous companion binary by assuming an axisymmetric potential of the Milky Way potential. And yeah, so this is an example of a motion of a black hole binary, and we tracked the motion from black hole formation to present by assigning kick orientation randomly. Okay, so here is the result. And yeah, so we estimated comparable number of the result in the previous section, but I'd like to mention about the fact we employed more severe detection criteria, because the detection criteria I showed is super idealistic. So so the detection criteria were derived based on the assumption each binary parameter can be estimated independently. This won't be the case, because binary parameters should be estimated from ultimately luminous companion, the observations of luminous companion. So in order to explore the correlation between binary parameters, we have to include the effect of intrinsic parameter correlations, which is arising from the observations. So considering that the estimated value is somehow smaller than expected from the previous work, so but why can we estimate a larger number of detectable binaries? So that is because we employed meteoricity distributions and considered star formation histories, which is different from the previous work. And yeah, so we generated some binaries with lower meteoricities, which allows us to get more black holes. So that is the reason why we get more black hole binaries here. And finally, I'd like to share some notable correlations. And first is black hole mass and the distance from the galactic plane. So these figures show the relationship between black hole mass and the distance from the galactic plane of the detectable black hole binaries. And so the size of markers is reflecting weight assigned to the binaries. So if the marker is larger, the weight is heavier. But yeah, but you can see in this lower mass gap region, we can see the detectable black hole binaries only in the delayed model, and we can't see any black holes in the rapid model. And also, the relationship between black hole mass and the distance from the galactic plane show anti-correlations in the delayed model. On the other hand, the correlations show positive correlations in the rapid model. So that is because in the delayed model, light black hole binaries can be kicked away from the galactic plane, and they can move away from the galactic plane. So thus, these correlations between black hole masses and the distance from the galactic plane can prove the black hole formation model. So this is the final result, and these figures are showing the relationship between orbital periods and eccentricities. And as you can see, so this is a model with the delayed supernova model, and in the left figure shows the model with fallback kick, and the right figure shows without fallback kick. And we can see positive correlations with fallback kick model and anti-correlations without Natal Kick model. So we also concluded correlations between orbital periods and eccentricities depend on the choice of kick model. Okay, so it is the end of overviewing our papers, and I'd like to mention about the possibility of the future observations with Gaia. So in the latest data release from Gaia collaboration, 2 black hole and luminous company binaries are confirmed as Gaia black hole 1 and 2. And I summarized some binary parameters of them here. And as you can see, the orbital period is longer than what we've seen in X-ray and gravitational wave observations. And these papers discussed such wide orbits cannot be formed in the isolated field, but in dense stellar regions such as open clusters. So I hope one of our papers should have a big impact on the formation of these detected black hole binaries. And also, there are some other candidates of black hole binaries reported in these papers. What is interesting is that they include some mass gap black hole candidates. So if they are confirmed as black holes, it should be also a big impact of black hole formation. So I hope as more black hole binaries are detected, theoretical studies, including ours, will be validated. Okay, so this is the end of my talk, and here is my summary. So in this talk, I showed some results of our theoretical researches, and we found several to tens of non-interacting black hole binaries can be detected with Gaia. And also, we obtained some important implications for the observations. And we hope these theoretical studies should be validated in the near future. So, okay, thank you for listening.